what's called the Calabi-Yau quintic threefold. That's the famous, if you go to the Wikipedia page for string theory, that's one of the images that appears. That's the Calabi-Yau threefold. And in preparation for this course, I forced myself to learn how to draw these beautiful bastards. So I wrote a little code, so if you're familiar with Python, this might might make some sense to you. If you're not, that's okay. So let me just run some of this code. So there's I'm very happy to share this file with anyone who wants to tinker with this on their own and explain. I've written a lot of comments. So we are going to generate an image of this very famous Calabi-Yau quintic threefold, which is the Fermat quintic, which is literally given by this fifth degree polynomial equation in the projective four space. So it's this is strictly speaking. So this is a four-dimensional, complex four-dimensional space, and inside there I'm taking a hypersurface, a complex hypersurface. So this is really a complex manifold of dimension 3, complex dimension 3. So obviously there's no way we can draw anything like that. But what we can do is we can take like a slice, a complex two-dimensional slice by setting some of the variables to be some kind of constant, and then we still get a 2 complex dimensional thing, so a 4 real dimensional thing. Still can't really draw it, but there's a kind of, some people have come up with ingenious ways of drawing, kind of filling it out with 2-dimensional complex slices. Two-dimensional real slices, so Riemann surfaces, and putting them together, and you get this kind of nice image. If I have time at the end, I'll explain in more detail how to draw this. And even if I don't, if you're really interested and want to impress your friends, impress your friends how to draw this, then speak to me during the week. I'll be very happy to explain to you how to do this. I've also written this little applet where we can, let's see how many takes to do it, okay, where we can sort of swirl it around, have all these nice different angles. You can go inside the Calabi-Yau manifold, have a little look around. It's nice. Come back outside. Oops. Anyway, so this code, I think I'll put this up on the website, and anyway. So that's this famous example. We'll get to it. But I want to kind of, I understand that the backgrounds are really quite different here. So I want to start with something quite basic. I'll literally start with the definition of a complex manifold. So I want everyone to come out with at least some hard skills out of this mini course. It will naturally accelerate as we go along. Right, okay, so that's enough of the nice pictures. Get my notes. Any questions so far? Yeah?
Does the color encode something? Because like just 3D plus color makes 4D? Or?
Yeah, so as I said, the way you draw it is like you fill out the two-dimensional complex manifold with Riemann surface slices, and each one of those I call a sheet. And so you just basically, it's the same Riemann surface but rotated by a phase, and so the colors are the different phases. So it's like imagine if you want to draw a cylinder, one way to draw it is to draw a bunch of slices. So that's exactly what I'm doing here. It's a bunch of slices which together fill out a two complex dimensional manifold. That's the idea, yeah. But ultimately the colors are just there for aesthetics. Right. Okay, so the plan is I'll start with complex manifolds and we'll do lots of examples, and then I'll try to explain what a canonical bundle is, and that should be enough for us to kind of get into Calabi-Yau manifolds proper. Okay, so let me start. So section 1, complex manifolds. So you may be familiar with the notion of a manifold altogether, or at least have heard of it. A manifold, in the real sense, is a space that is locally modeled on Rn, right? So locally it's an Rn, and then you glue them in some weird way to get something interesting. complex manifolds, it's the same thing except you model it on C to the n rather than R to the n, that's all. So, no mystery. So definition, so let me start with X, a topological space. And so I will say that an n-dimensional complex chart on this topological space X is a homeomorphism let me give it a name, phi, from an open subset U of X to an open subset V of C to the n, so where U of X is open and V, which is the image of U under phi, and this is an open subset of C to the n. That's it. It's just a homeomorphism to C to the n. So, maybe an image, a picture. Let me draw it here. So here's my nice looking topological space. Here's my C to the n, which suspiciously looks like C. And I take an open set here, which is some kind of blob, call it U, and I have a homeomorphism phi, which maps to some open subset, which I've called V. Notice that in this description, a priori X, there's nothing complex about X at all. Right? I'm not saying that this is some kind of holomorphic map or anything, that's not the point. The point is that this is just a topological space, you only have topology, no geometry, but you have a homeomorphism to a subset of C to the n, which does carry all the geometry that we need. And so the idea always is that because we have these homeomorphisms, these charts that map to C to the n, all the geometry that we need, all the complex structure that we need, we're just going to pull it back using these homeomorphisms. So in other words, another way that people say this is that we're going to equip X with a complex structure such that this homeomorphism becomes a holomorphic map. It's just another way of saying that we're literally just taking the complex structure from C to the n and just taking its pre-image. So why is that useful? In particular, it's because now, now that we are mapping everything to C to the n, we can compare two different charts and see if they agree on the complex structure that they pull back. So I will say that two complex charts, let me call them phi alpha. Actually, I want to draw this. I want to write this on the next page. Sorry. This one. So, two complex charts, phi alpha and phi beta. I will say that they are holomorphically compatible so they both map to C to the n, so I can compose, or take their ratio as I like to say, compose one with the inverse of the other. That gives me what is called a transition function, so that the transition function which I will call phi alpha beta, which is phi beta compose phi alpha inverse. And so what's the domain and the codomain of this map? So it goes from the codomain of phi alpha, which is of course the V alpha or the image of U alpha. But I need to be able to make sure that once I get back to my complex manifold X under this inverse map, I need to be able to compose it with phi beta. So I better make sure that the codomain, sorry, that this domain intersects the domain of phi beta. So the way to do it is, of course, to just look at the intersection. So this is a subset of C to the n. I mean, this whole thing is a subset of C to the n. And what does it map to? Well, it maps to wherever phi beta takes this to. U alpha intersect U beta. This is also a subset of C to the n. And by the way, a priori, these two, although U alpha and U beta, I'm implicitly assuming here that this intersection is non-empty. The images under phi alpha and phi beta of this double intersection, they may have nothing to do with each other. They may be completely disconnected, and that's okay. So let me draw this, just so that you have an image of what's happening. We use green. So maybe I'll call this U. This is going to be my U alpha. U alpha. This is my V alpha. And then at the same time, I have another open set, which I've called U beta. And that thing also maps to C to the n. So here's another copy of C to the n. This is the image under phi beta. Right? And what I'm interested in here is, maybe I'll draw that red, is this intersection. This is the intersection U alpha intersect U beta. And so as I mentioned a priori, here's the image of this double intersection under phi alpha. And here's the image of that same double intersection, but under phi beta. And so what this transition function is really a map from an open subset of C to the n to some other open subset of C to the n. So this is my phi alpha. And so the requirement for these two complex charts to be holomorphically compatible. So if you're familiar with differential geometry, you would say that two charts are like smoothly compatible if this is a diffeomorphism. It's an invertible C infinity map whose inverse is also C infinity. So in complex geometry, exact same story, except we replace the word C infinity or diffeomorphism with holomorphic. So this should be a biholomorphism or holomorphism. Holomorphic bijection with holomorphic inverse. Does this make sense? Any questions? just going to give you a second to absorb this. If you've studied differential geometry before, this will seem very natural. If you've not, this may be like a lot of information, but really, you just need to think that we're just mapping bits of our topological space to C to the n, and we just want to make sure that we do this in a compatible fashion. So if I go from one chart to another, I preserve the holomorphic structure. All right. Okay. So definition. So a complex manifold of complex dimension n. So in this mini course, whenever I say dimension, I always mean complex dimension. If I need to refer to the real dimension, I'll explicitly say real dimension. So of dimension n is, well, it's a topological space, and I need a few properties on the type of topology it can have. They're not. I don't want to overemphasize this. You could say they're slightly technical. I'll include them anyway. So it's a second countable Hausdorff, and I'll also include connected, although this is far less common. Topological space. X, which is equipped with a complex atlas. What's a complex atlas? It's just a collection of complex charts which cover the entire topological space, which are holomorphically compatible amongst themselves. So it's a collection of holomorphically compatible complex charts. Let's say enumerated by alpha. Alpha doesn't have to be finite, or it doesn't even have to be countable. It could be an uncountable. I mean, usually it is an uncountable index set. All of these V alphas are subsets of C to the n. So such that, so if it's an atlas, it better cover the entire space X. And so the way I'll write this is that such that if I take the total union over all alpha, of all these open sets U alpha, this gives me the whole topological space X. How does that sound so far? Yeah.
Why do you want the connectedness of the space?
So that's not really important, but usually you could say it's, especially when you start computing cohomology of manifolds of various kinds, it's just simpler if the whole thing is connected, and if it's not connected, you just treat them as two separate things. So it's not very deep. It's just more of a technical assumption. Also, if I see two manifolds, I think they're two manifolds, right? So, okay, so let's jump into a bunch of examples. So example number 0 is the one we've already sort of thought about extensively, which is the Euclidean space. c to the n itself. That is a complex manifold. So what are the type of things I should say about this? So first of all, it has a standard coordinate chart, which is the whole space. So standard coordinates. Standard coordinate chart, which is, you know, you could say it like this, phi c to the n, c to the n. What it does is it takes a point and just outputs the same point. So it does nothing. It's the identity map. It's a global chart. So when we say global chart means that it's just one complex chart, but it covers the whole manifold. This is not true of all complex manifolds. Many complex manifolds do not admit global charts. We'll see such an example. So there's another structure that I want to mention right away, which we'll use a little later in the course. So one thing you can note is that you know, all these coordinates, or all these coordinate components, Zi, you always can decompose them into the real and imaginary parts. So always have the decomposition. Zk xk plus I yk, where these x and y are the real coordinates. So that means that every complex manifold of dimension n has an underlying real manifold of real dimension 2n. So if you literally just forget that we have agreed to combine some of these, pairs of these real coordinates into such a combination, x, xk plus I yk. If you just forget about the fact that we make this arrangement, you're just forgetting the complex structure, and you're ending up with the completely standard notion from differential geometry of a complex manifold. Sorry, of a real manifold, real smooth manifold. That's what maybe I should say. Real smooth manifold. So okay, let me say a couple of other things. So now suppose, like when I give you c to the n, that implicitly comes with a standard coordinate, which is how you encode c to the n. It's the collection of these tuples. But I could change the coordinate, right? So I could make a change of coordinates on the c to the n, or I'll have a different copy of c to the n with different coordinates, and I can study what that change looks like. So if I give myself another coordinate, which maybe I'll call w. So that means, in this new language that we're developing, I could say that I'm giving you another global chart, another global complex chart, which maybe I'll call phi 1. Maybe I should have called the previous one phi 0. Sorry, so let's call this one phi 0. I'll call that one phi 1. So what does that one do? It takes c to the n. So c to the n, so it takes a point which I am enumerating by the tuple z, and outputs some some function of z. So phi 1 of z, and this is what I call w, some vector function of z. So now I have two complex charts. Nowhere in this discussion is it obvious that they form the same complex atlas. That's something that I need to check. What does that mean? It means that whatever this function is, w, maybe I should write w of z, this function better know, better respect the holomorphic structure. So the transition function is, so what is it? It's phi 0, 1 of z, and that is the ratio of phi 1 and phi 0. And, well, that is exactly this function, whatever this function I came up with. And so that means that if I give you if I give you another global complex chart, which I call W, for it to be holomorphically compatible as a function of Z, as a function of the old chart, this better be holomorphic. That's what it means to be holomorphically compatible. So phi 0, phi 1 are holomorphically compatible if and only if W of Z is holomorphic. Holomorphic and its inverse, which I suppose you could write as Z of W is also holomorphic. However, the one beauty of complex analysis is that there's a theorem, which is that if I have this function, vector valued function, which is holomorphic, and if I can prove that it is invertible, so it's a bijection, then that automatically implies that the inverse is also holomorphic. That's how rigid holomorphic geometry is. Any questions?
About this. Would the complex conjugate be such an example?
Yeah, exactly, right. So very good, excellent question. Correct, yeah, so exactly. One example, so maybe I'll leave this as a quick exercise. So the exercise, I'll formulate it like this. So notice, this discussion means that, I'll write it like this, that c to the n with phi 0 of z equal to z is a complex manifold of dimension n. So another thing that you could check is that if I take c to the n, the set of n tuples of complex numbers, and equip it, now I don't know what to call it, let's call it psi, with the following complex chart, which is that I take the point z in c to the n, and I send it to its complex conjugate. So just every single, does this make sense? This just means like this. So check that this is also a complex manifold. Right? Don't get distracted by the fact that I've included complex conjugates. This is still a homeomorphism to c to the n. So I can grab the complex structure from c to the n, which corresponds to the conjugation, or whatever. I can grab the complex structure of c to the n, conjugate it, and pull it back, and that's how I'm equipping this copy of c to the n with the complex structure. Now the real check is that phi 0 and phi 1, and psi 0 are not holomorphically compatible. So these are genuinely two different complex manifolds. This one is sometimes called the mirror of this one, just because we're using the complex conjugate. Thank you for that question.
Sorry, but I didn't really get it. Because in the definition of your complex manifold, you need so a set of holomorphic compatible complex charts.
That's right.
In the case of the complex conjugate, you have only one chart.
That's right, and that's enough. I mean, right? That's,
I know, but to me, complex conjugate is not holomorphic.
That's true. That's true. It's not holomorphic with respect to the usual complex structure in C to the n, right? But if I take the opposite complex structure, which is what I'm suggesting you do here, then just imagine. Suppose you do a change of coordinates, right? So I have a function of z bar, and I just need that function to be holomorphically compatible. So in other words, it should send z bar to a function of z bar, and that map should be holomorphic. So it should satisfy Cauchy-Riemann equations, and you will find that that is the case.
Right, I get it.
Very enthusiastic.
Yeah, he doesn't like the mirror structure. Anyway, very good question as well. Yeah, it's a very good exercise. It looks kind of completely innocent and very simple, but it can be kind of confusing. So it's actually a really good exercise to think through. Again, thank you for that question. Very good. I'll give you another second to absorb. By the way, someone should tell me when the break is supposed to happen, because I have no notion of time. I live in a complex world.
But you know, don't worry.
Right, okay, so let me do another example. This one is going to be example 1. And that is, I'll call that complex torus. The notation is, the notation that I use is Blackboard T sub lambda, and it's basically the quotient of c to the n by this lambda, which is a lattice. So here's how this goes. So first, choose any 2n complex, non-zero complex numbers, and call them lambda 1 down to lambda 2 to the n. So these are, sorry, not complex numbers, vectors. Complex vectors in c to the n. So I just want them to be non-zero. And okay, let me switch backwards. So these guys generate what we call a lattice. Consider the lattice, which I call lambda. And what it is really is the integer span given by these vectors. So it's the span of all these lambdas. Lambda 1 down to lambda n. Sorry, what am I saying? Just this is what I want. So this is a subset of c to the n. So again, let me be completely explicit. So these are tuples, all the tuples z, which are integer linear combinations of lambdas. Like this. Okay, so what do I use this lambda for? I use it to define an equivalence relation on c to the n. And basically, the equivalence relation is very simple. If I have two vectors in c to the n, and I take their difference, if that difference lies in this lattice, then I call those two vectors equivalent. So there's an equivalence relation on c to the n, whereby I have, what did I call them, z and z prime. So these two things are equivalent if and only if their difference lies in lambda. And then we define complex torus as the quotient. Or
Is there a question?
sorry, yeah.
Don't we also assume they're linearly independent?
No, you don't have to.
Okay.
You may want to, in order to get good properties for these complex tori, but you don't need to. So yeah, so this complex torus is really just the set of all equivalence clauses. So in other words, how do I want to write this? Just including several, maybe different notations, whichever one you're more comfortable with. Okay, so let's draw some pictures. So let me just focus on the case n equals 1. That one's the simplest, and also will tell you exactly why I call this a complex torus. So, for example, for n equals 1, so let me draw, here is my copy of C. And so for this case, n equals 1, so I just need to choose two vectors in C. So let's say this is the origin in C. And let's say the way I chose my vectors is something like this. So this is lambda 1, lambda 2. And now what I have is I use these vectors to generate a lattice. So all the integer linear combinations of these, so that in particular includes 0, but also includes stuff like 2 lambda 1, and also minus lambda 1, etc. And similarly, lambda 2, and it also includes 2 lambda 2, and minus lambda 2, etc. And all the, so this one is, for instance, very important. Lambda 1 plus lambda 2, and all the other combinations. So what you get is this, well, what we call a lattice. An integral lattice. Etc. And so what's going on? Why am I interested in this lattice? So let's say I look at this point. So this is my point Z. So according to my prescription, if Z and Z prime differ by something in the lattice, then I identify them. So for instance, if I look at this point, which is Z minus lambda 1, right, the difference between Z and Z minus lambda 1 is lambda 1, or whatever, minus lambda 1. And that belongs to the lattice. So I identify these 2 points. Similarly, if I look at this one, which I'm thinking of as Z minus lambda 2, again, I have an identification between this point and this point. And in fact, between this point and this point. And so what you can see is, you know, if I draw this parallelogram here, then what is happening is that all the points inside this parallelogram, they kind of get repeated all across the complex plane, and they're all identified with each other. So if I'm only interested in the space of equivalence classes, I may as well just focus my entire attention on this parallelogram, because everything else is just the translated copy of it. And so the image that you're looking at is essentially this blue parallelogram is essentially the complex manifold T lambda, with one slight complication, which is that, you know, let's look at the boundary of this parallelogram, and let's say this point is identified with this point, right? So you know, I drew this parallelogram as some kind of open subset. That's why these things are dashed. And so I, technically speaking, didn't include these boundary points. And that was on purpose, because if I did include them, then suddenly this is not a one-to-one corresponding image of this manifold, because I have duplication inside my chart, right? So I have to be careful. So, but anyway, okay. If I look at this, what I see is that this point is identified with this one with this one, etc. And so what I have is that these sides are identified, and these sides are identified. And this picture hopefully rings a bell, because this is exactly how we describe a torus, a real torus. So when n equals 1, this complex manifold, the underlying real two-dimensional manifold, is literally your familiar donut. And then, you know, you could say that this is topologically speaking, this is S1 squared, the product of two circles. And so I'll make this as a remark. So topologically, this T sub lambda is 2 to the n. Yeah.
Again, trivial detail, but you have to also assume that they're linearly independent for this.
For this, yes. For this statement, yes, absolutely. Otherwise, indeed. So
It's a cylinder,
if
then.
some of these start to align, the topological picture is that some of these handles start getting pinched. Yeah. Okay, so the last thing I want to remark about this, or maybe the penultimate thing I want to remark about this, is that this is your first example of a complex manifold where a single global chart doesn't exist. Like, what would I need to do? I need to be able to cover this entire this entire parallelogram with an open set that gives me a true one-to-one image to the complex plane. And so, you know, I can use this open parallelogram, but that excludes the boundary, which are points in my complex manifold. But as soon as I make this thing any bit larger, then I get a duplication of points. So here, you know, in order to cover this with complex charts, you really need to use several to kind of layer over this parallelogram. A single complex chart won't do. Good. Makes sense? Maybe one more thing to note. Again, for this, maybe the easiest is to recall back to your kind of topology. If you use this fact, then you can see immediately that all these complex tori constructed this way, they're all compact manifolds. So this is your first example of a compact complex manifold.
And how would you go over the boundaries of these parallelograms?
Well, you know, one way is to do something like, like do like one patch like this, another patch like this, and make sure that all of these patches, they're kind of strictly smaller than a single parallelogram, so you never get a duplication. So in this case, I guess you need maybe at least 4, I would reckon. All right. Next example, unless there are any more questions about this. Okay, next example, super important, is the complex projective space. Which I always denote by the n. You may be more inclined to write it as CP okay, so what is this? So in one word, or in a sentence, this is the space of all complex lines. By a complex line, I mean a one-dimensional complex vector subspace. So all complex lines through the origin in c to the n. C to the n plus 1. So in other words, let me write this in formulas now. So p to the n, again, it's defined as a set of equivalence clauses. You can see a theme. Most interesting complex manifolds are defined in this way. So yeah, so you need to remove the origin and mod out by an equivalence relation where, so if I have a point z, point in c to the n, non-zero point in c to the n, so it has coordinates z naught, z1, up to zn. This is equivalent, this is my definition, this is equivalent to multiplying by a scalar, a non-zero scalar, multiplying every single coordinate by a non-zero scalar, which I'll call lambda. So that's the definition. So equivalence classes have a notation, useful notation. So the equivalence class of a point z, a vector z, is, we often write it in this form. So this is, you could say this is a line through z hat in c to the n. So I don't know if an image would help. So here's the image. Here is my c to the n. Here's my origin. Here is my vector z hat, which is just a point in this space. And so what you should think of as a point in e to the n is this line. So this line is literally the point in p to the n. And it's labeled like this, and we refer to this often as homogeneous coordinates. Very important object. So these homogeneous coordinates, because it's an equivalence class, the equivalence class is given by the ability to rescale all the coordinates by a single scalar. In particular, if z naught were non-zero, then I could use, I could define lambda to be like 1 over z0, and so rescale all the coordinates such that the first entry in this tuple is just literally equal to 1. This is the kind of thing that you do all the time in the projective space. So I'll just write this as a kind of a bunch of observations. So observe. So if, for example, z0 is non-zero, then this tuple z0, z1, down to zn, this is equivalent, under our equivalence relation, to one where I just divide by z0, or multiply by 1 over z0. Or in other words, the way I would write this using homogeneous coordinates, as I always do, is that this point with, the point with homogeneous coordinates z0 down through zn is the same point with homogeneous coordinates 1, z1 over z0. That's down through zn over z0. And the cool thing is that you see, when I write homogeneous coordinates like this, I have n plus 1 complex numbers that I need to give you. But that data that I would give you is ambiguous because I can rescale them all by lambda, right? So if I give you a particular set of n plus 1 complex numbers, that is an ambiguous information. However, if I insist that one of them is equal to 1, right, or maybe, let me phrase it like this. If I insist that one of them is not 0, then I can rescale them all to set that particular coordinate to be 1. And then that eliminates the ambiguity, that eliminates this freedom of rescaling, right? Because any further rescaling would ruin this 1. So now, suddenly, by restricting my attention to the case where z0, let's say, is non-zero, and rescaling z0 to be 1, I now have established n complex numbers, these complex numbers, which are fixed. There's no more ambiguity. And what that defines for you are very important complex charts. We call them affine charts on P to the n. They're extremely important. So let me describe them. So this is a famous open cover by what we call affine charts. So I will call them U sub I. And so what is this? This is a subset of the complex projective space, P to the n, where I restrict the attention to the case where the ith entry in this tuple is non-zero. So, okay, so a few remarks that I need to make about this. So, okay, so first of all, it's you can check that it's open. I mean, it's given by, it's given as the complement of an equation. This is an equation, right? And as usual, complements of equations are ordinarily open sets, and this is not an exception. But maybe it's worth for you to check it on your own. So the other thing that I want to check, the other thing that I want to explain is that if I have a point in C to the n plus 1, which is non-zero, then because I insist on the fact that this point is not the origin, that means at least one of the coordinates of that point have to be non-zero. And so what that shows is that any point in P to the n, which is represented by a tuple like this, necessarily has at least one entry which is non-zero. So that means that every point in the projective space must lie in at least one of these open sets. So in other words, these affine charts UI, the collection of n plus one of them, give me an open cover. So P to the n, I from 0 to n, to n. Okay, so now I have an open set. In fact, I have a covering by open sets of P to the n. This is beginning to sound like an atlas, so let's make it so. So my complex chart is going to be like this. So it needs to be a homeomorphism from UI, from one of these open sets UI, to a subset of C to the n. Well, in fact, it is homeomorphic to the entire copy of C to the n. And the way it goes is very simple. So if I pick a point like this, so it's a point in UI, right? So that means Zi in this tuple is non-zero. So that means I can rescale the whole tuple to set the ith position to just 1. So that's what I will do. So I have Z0 over Zi, Z1 over Zi. Sorry, these are supposed to be colons, as usual. Up to, there's Zi over Zi, which is obviously just 1. And then it continues down to Zn over Zi. So these are different representations, but they're the exact same point in P to the n. So now I'm going to define where I'm going to send this. Well, there's only one real, really decent option, which is just whatever this coordinate, this ith position 1 is, just leave it out, and you're left with now not n plus 1, but n complex numbers, and that's the complex number. That's the complex vector I'm interested in. So I'll call that maybe W1 through Wn, which is just Z naught over Z1 down to, I'll write it like this, Zi over Zi, this is the one I leave out. The hat means leave it out. Down to Zn over Z, this is supposed to be I. Right, and so this is a point in C to the n. And so an exercise, you can check that this is indeed bijection. And so therefore it's it's an open, it's a continuous bijection. So it's a homeomorphism, in other words, is what I'm trying to say. It's a homeomorphism. And so now, I've defined for you P to the n really as a set here. It's a set of equivalence classes. But now I'm really claiming that this is a complex manifold of dimension n. And the truth to that answer lies here. This is how we establish that this is this is the definition of a complex structure on this set, on this topological space. Does that make sense? Okay, so let's see how much of this I want to say. So I said, this is how we establish that it's a complex manifold. Okay, I've given you a bunch of complex charts. Of course, in order to check that they define a complex manifold for me, I need to check that they form a complex atlas, which just means that they are holomorphically compatible. So this is a calculation that is worthwhile doing in the safety of your own PC. But I'll describe some of it. So the transition function, just to give you a flavor. So let's say in the case n equals to 3. Is that the one I want to do? Yeah. So let's see. So how would this go? So when n equals to 3, sorry. This is my, no, I guess I want n equals to 2. Sorry. So this is the homogeneous coordinates, and let's say I'm looking at the double intersection u0 and u, which one did I do? And u1. So on the one hand, I'm in u0, which means z0 is non-zero, so I can rescale it away. And so I will get z1 over z0 and z2 over z0. And so what my prescription, so the chart phi 0, what it does is it sends it to the pair of numbers w1, w2, which are just these two complex numbers. Z1 over z0, z2 over z0. Right? On the other hand, I'm also sitting inside the affine chart u1, which means z1 is a non-zero complex number, so I can scale it away to be 1. And so I can rewrite this thing as z0 over z1, 1, z2 over z1. Right? And similarly, my prescription, in this case it's the chart phi 1, the prescription says drop this middle coordinate and just extract. Now I will call them maybe w1 tilde, w2 tilde, and just get the two non-trivial complex numbers, z0 over z1 and z2 over z1. Right? Okay. Okay, so what's the transition function? So let me just say, let's kind of follow this diagram, but going from here to here. So we have w1, w2. So under the inverse of this chart, so phi naught inverse, I'm supposed to send it to a homogeneous coordinate where the first entry is 1, and then I place the two complex numbers that I picked myself. Right? Okay. Now I want to use, so this is my phi naught inverse. I want to now compose it with phi 1. Right? So for phi 1, I better rewrite this homogeneous coordinate in a more convenient way, right, to use the formula for phi 1. And so that means what I want to do is I want to set this middle guy, w1, I want to rescale the whole thing to set that to 1. So what I need to do is I just need to take all these numbers and divide by w1. So I get 1 over w1, 1, w2 over w1. And now I can just apply the formula for phi 1. And so this is my w1 tilde, w2 tilde, now as functions of w1, w2. And what are they? Well, it's 1 over w1 and w2 over w1. And so, okay, is this holomorphic? Is this a holomorphic map? This is the next question that we need to ask. Well, there is a kind of suspicion that falls on it because w1 appears in the denominator, right? So that sounds dangerous. But the fact of the matter is, we need to pick w1, w2. Where? Where do we need to pick it? We need to pick it in the image under the chart phi naught, of the double intersection U0, U1. Right? And, well, what is this thing? Let's see. So, well, I don't know if it's, maybe it's obvious. Is it obvious that this, anyway, maybe I'll let you think about this. I mean, it's just kind of tautology, right? You just, anyway, so the point is that because we've restricted our attention to this double intersection, its image under phi naught is precisely the thing, it's precisely the open set of C to the n, open subset of C to the n, which ensures that this has no problem, right? And you can then see also that this guy falls inside the image of the double intersection under phi 1. And again, if you squint your eyes, you'll see that what this thing is that it's W1, W1 tilde. W1 tilde is non-zero. Which, if W1 is non-zero, this first entry is definitely non-zero. So,
Life is good.
life is great. Yeah, it's like knife through butter. No, knife through Swiss butter. Yes.
So I have a question about your image where you say that this equivalence class is just a line through Z in Cn. So if you allow lambda to be any complex number except 0, this line can also be rotated. No? So if you're in 2 dimensions, then this line is actually the entire complex plane, right?
Yes, that's right. Yeah. So you're thinking of C mod the equivalence class, or C.
Exactly. Yeah.
And indeed, that
So
is
if you're in C2,
that is the point.
It's just the point. Okay.
Exactly. It's just the point. So that would give you P0.
Right.
P1 would be C2, two-dimensional complex space, two complex dimensional complex space, mod equivalent class. And that one is your usual, familiar P1, CP1, that we're so familiar with, and so on. Yeah. But indeed, yeah, P0, you just prove it yourself is a point. Whether or not you want to consider a complex manifold is up to you, I suppose. Questions? Any more questions about this? Okay. So, what else do I want to say about this? So let's draw a few more pictures. So maybe I'll just say this in words, an exercise, just redo this calculation. I did it for n equal to 2, but try to find the formula for the transition function for arbitrary n. It's not so complicated. But it'll force you to delve slightly deeper into this space. It's a good exercise. Okay, so another note. Not obvious. One has to really check this. But P to the n, this space P to the n, is compact. It's a compact complex manifold. So as I said, it's not an obvious fact. You really need to check this. But one case in which it is kind of visibly true is when n equals to 1. So let me review this. So some of you have seen this, and so this will be a good review. So in particular, on P1, which is now, so it's the set of homogeneous coordinates which have just two entries, Z1 and Z0 and Z1. And so there are two charts, two affine charts. Two affine charts. So there's U0, which is the place where Z0 is non-zero. And so that means when Z0 is non-zero, I can always scale it away, and I end up with a single complex number, which is Z1 over over Z naught, and I'll call it Z. So you could say it like this. It's the collection of Z, which is related to these coordinates by Z1 and Z naught. This is a complex number, not necessarily a non-zero complex number. Could well be zero, right? I'm restricting Z naught to be non-zero, but Z1 is free to be zero. And so, what this formula is showing, I'm just kind of compactifying the things that we've written more explicitly before, but this is really just my complex chart which equates this set with C. So my first, this affine chart U0 is just a copy of C covering some part of P1. Similarly, you have the U1 chart where Z1 is non-zero. And so I can play the same game. This is, this is a set of complex numbers. In this case, maybe I'll call this W, this new coordinate W, which is Z naught over Z1, which incidentally, well, so this is C, this is giving me the isomorphism with C, and the transition function over what? The transition function over the double intersection, the only one double intersection that we have in this case, which is U0, U1, is really just, I don't know how you want to write it, as W of Z. It's the inversion map. It just takes Z and flips it. Why does this make sense? Well, because U0 intersected with U1, what is this set? It's the set, so first of all, it's the set where Z is non-zero, right? So that cuts out a C star inside this C. And similarly here, it's the subset where Z1 is non-zero, and so that means, it's the subset where Z1 is non-zero, but also Z0 is non-zero, so that means W is non-zero. So that cuts out a C star inside this copy of C. So this thing is really isomorphic to C star. Did this make sense? So let's, so we have, basically what we have is, we have two copies of C which intersect along a C star. And somehow they get put together to give me a complex manifold. So let's try and draw this. So the helpful way to understand this is to view both of these copies of C as a kind of two caps, or two sort of disks which overlap in a infinitely thick band, and they overlap to give me a sphere. So the picture is like this. So I have this is my P1, like this, and it's homeomorphic to S2. It's just a sphere. And the way I got this is by, well, taking two of these copies of C and gluing them along a C star. So this is how I'm going to view it. So I have one copy of C, which I picture again as a sphere, but with a point missing. So this point, so this is my U0. Remember that this is the complex plane with coordinate z, and the only point that's missing is what I would call z equals to infinity. It's the point at infinity that's missing. Or another way you could say this is that this is where w equals 0. That's the point that's missing. And so I have two such things. So in this case, it's z equals to infinity that's missing, and in the other copy of C, so this is my U1, which is C with coordinate W. It's the opposite point that's missing, which is which is w equals to infinity, or in other words, z is equal to 0. Yeah, z is equal to 0. And so what they intersect in, so U0 intersect U1 is just a sphere with 2 points missing, like this. And the reason I was referring to it as a cylinder, so this is a copy of C star, is because, topologically, the fact that these points are missing, that these missing points are points, topologically is kind of immaterial. So what I can do is I can sort of wind them up however I like, and so I can picture this thing as an infinite cylinder with, with this boundary missing, like this. So that's why we call it a cylinder. Does this make sense? How are we doing with the break time?
You have 8 more minutes.
Oh, perfect. Okay, so maybe I'll end this half lecture by pointing your attention to a very, very famous open problem in mathematics, which with every fiber of my being, I encourage you not to embark upon. The reason being that many mathematicians have fallen on their sword whilst trying to solve this problem. There is a bazillion number of papers, both preprint, archived, and published papers in quite good journals, which are wrong. So it begins with just noticing, so note. So here I kind of pictorially explain to you that P1, so in other words the projective space for n equals to 1, the one-dimensional projective space, is topologically, in other words the underlying topological manifold is homeomorphic to the 2-sphere. So fact is that if I look at any other projective space, your initial guess might have been, P2 is then homeomorphic to like the 4-sphere or something like that. But that's not. So for all n not equal to 1. So it's not an obvious fact. In order to prove this, I mean, it's not difficult, but you need to kind of compute cohomologies of these spaces, and then it becomes clear that this cannot possibly happen. But this is not a course about cohomology, so the problem that I wanted to mention is about, fine, these are complex manifolds. They are not the 2n spheres. What about 2n spheres? Are all 2n spheres the underlying manifolds for some complex manifolds, right? So if I take the 4-sphere, S4, we know that S2, as this example shows, S2 is a manifold, a topological space that underlies a complex manifold. What about S4? What about S3? So, obviously you can immediately eliminate all the odd dimensional spheres, so like S3, S5, just because, as I mentioned at the very beginning, any complex manifold is necessarily an even dimensional real manifold. So just by dimensionality reasons, an odd sphere cannot be a complex manifold. But what about the others? So in fact, this is a kind of striking, weird fact. So if I look at S to the M sphere, so the fact goes like this. The M sphere cannot be the underlying real manifold of a complex manifold. It cannot be a complex manifold for any M except, and this is the odd thing, except M equal to 2 and 6. All the other ones we can prove, not necessarily in the most straightforward way, but it can be done at a graduate level sort of differential geometry course, that this is the case. For m equals to 2, we know that it does admit a complex structure. We've just seen one. Does the sixth sphere admit a complex structure? Famous open problem in mathematics. It's called Hopf problem. So famous open problem. It even has a name. That's how famous it is. It's called the Hopf problem. Can S6 be a complex manifold? We don't know. We just don't know. And if you have absolutely nothing else better to do with your life, you can Google this problem, and you will find a bunch of papers which claim to have proved that S6 does not admit a complex structure. And all those papers, the last time I checked at least, all those papers are wrong. They all contain some kind of non-trivial but fatal flaw in their proof. So they're just not proof. And also a bunch of papers which claim the opposite, that they claim to have constructed a complex structure on the sixth sphere. And they're also wrong. They have flaws which they kind of completely destroy the whole construction. It's an irreparable. So to this day, we just don't know. So maybe this is a good time for a break. Given as the zero locus of a homogeneous polynomial. So I'll call it X, and it's the set of points in P4 labeled, I'm giving you the homogeneous coordinates of this point. And these homogeneous coordinates have to satisfy this polynomial equation. So this polynomial, maybe I'll call it P of Z. So one thing to note is these are homogeneous coordinates for a point in P4. And remember, we discussed that these numbers, Z0, Z1, they're kind of ambiguous, right? Because I can rescale the whole tuple by a non-zero complex number, and that would give me the same point. And yet I'm giving you an equation that supposedly cuts out this complex manifold. I'm giving you an equation using these ambiguous complex numbers, Z1, Z0, Z1, Z2, etc. But make no mistake, this is an unambiguous definition. Reason being that this polynomial, although these monomials involve some kind of ambiguous quantities, all I need from this is that the whole thing equals to 0. And so if I were to study the ambiguity and rescale all the numbers by some non-zero complex number, what that would do is that would just, if I rescale everything by lambda, that, a lambda to the fifth would pop out here, and a lambda to the fifth here, and so the lambda to the fifth would pop out in front of every monomial, and so you can factor it out all together. You will have a lambda to the fifth in front of this thing, and then of course all I'm asking here is that the whole thing equals 0, but lambda is by definition a non-zero number, so it has no effect on the set of points that satisfy this equation. So this is why when you're defining complex manifolds as subsets of some complex projective space, it is important that the function that you use, in this case I'm using a polynomial, is a homogeneous polynomial. So the property that I just described, the fact that I can rescale all the z's by some lambda and this lambda just pops out, is the defining property of what a homogeneous function is. So note, so this x is well defined because P is homogeneous. So what that means is that if I look at P and I scale the point Z by for any non-zero lambda, then it has the property that lambda just pops out. So this is a homogeneous polynomial of degree 5. So that's why I'll have the 5th power in front. And so that means that although the values of this polynomial obviously depend, they are ambiguous because I can rescale by lambda, and so that will change. But the zero locus is unambiguous. So that's a very important property. Okay, so at least as a set, this thing is unambiguous. So now I'm going to give you an argument for why this is actually a complex manifold. So X is a complex manifold of dimension. So what is the dimension? So I'm defining it inside P4, which is a 4-dimensional complex manifold. And I'm defining it by giving it to you as a zero locus of like I'm using a single equation, so a single constraint, single complex constraint. This is a complex polynomial. So that means I drop, I have 4 degrees of freedom, and I'm eliminating one of those degrees of freedom by making this constraint. So I expect this to be a 3-dimensional thing. So it is indeed of dimension 4 minus 1, which is 3 last time I checked. So why is this a complex manifold? Well, because I'm defining it as a zero locus of a polynomial, I'm giving you a polynomial that cuts it out. The most typical way to check what are the complex charts, whether or not we have the complex manifold structure, is to use, just like in ordinary differential geometry where you have this type of stuff, you use the implicit function theorem. And so when you go to the complex world of holomorphic functions, there is the analog, the holomorphic implicit function theorem. The statement is almost identical. Anyway, so why? Because of the holomorphic implicit function theorem. What do we need to check for the implicit function theorem? For the implicit function theorem, what we need to check is we just need to look at the partial derivatives of my function, right? And make sure that those are invertible at points that we are interested in. So if I compute, if I look at this P and I compute the Jacobian of it, I'm denoting like this. So in other words, this is just del P by del Z I. It's the Jacobian, it's a Jacobian. So what is this? So if I differentiate this with respect to Z naught, all of these guys get killed, and I just get 5 Z naught to the 4th. And then similarly, I get 5 Z1 to the 4th when I differentiate with respect to Z1, and so on. 5 Z, 4 to the 4th. And so the fact of the matter is, when I use the implicit function theorem, I need to check the implicit function theorem in the vicinity of a point on this, that belongs to this set. And I just need to make sure that at any point on this set, at least one of these derivatives is non-zero. Then I will be able to use, for that coordinate, I'll be able to use, I'll be able to present this as the graph of a function that maps that coordinate and gives me a little kind of cutout. That's how the implicit function theorem works. And so, why is that true? Well, it's because these points, Z0, Z1, Z2, they are homogeneous coordinates, right? And by definition of the homogeneous coordinates, this this tuple from Z0 to Z4 is a point in C to the 5 without the origin. So at least one of them is non-zero. And so I'm guaranteed that as soon as I am testing this vector, or this Jacobian, at a point of x, at least one of these numbers is going to be non-zero, and so this is a Jacobian of full rank. So the implicit function theorem applies. Does that make sense? Right. Okay, and last thing that maybe I'll mention is that x is obviously compact. Why is it compact? Well, it's a subset, it's a closed subset of a compact space. P to the 4 is a compact manifold, which admittedly I haven't proved or explained, but we saw it in the case of P1, so it is believable. But this is just a closed subset of a compact space, so it must be compact. So does this make sense? And so this is a three-dimensional complex manifold called a quintic threefold. In fact, I mean, if I take any homogeneous polynomial of degree 5, not necessarily this one, something more interesting, that would give me a quintic threefold. And as long as that homogeneous polynomial is smooth, by which I mean this Jacobian evaluates to something of full rank at any point, I will get a complex manifold defined as a subset of P4. This one in particular is very famous because this is the type of equations that Fermat was studying, so that's why we call it the Fermat quintic. And the image that I showed you on my laptop, on my iPad at the beginning was the image of this Fermat polynomial, or rather some slice of it. Any questions so far? All right, so I want to now talk about, so now if you recall back to the definition that we are kind of aiming for, the definition of Galois manifolds, one of the main set of words there was complex manifold, so now we kind of have some idea of what that means. The other set of words at the very end was that this, whatever this complex manifold is, it needs to have a trivial canonical bundle. So what the hell does that mean? So let's talk about the canonical bundle. Of a complex manifold. So okay, so let's go back to the Euclidean space. So on C to the n with standard coordinates, Z1 through Zn. Just like in real differential geometry, you have differential forms, so local coordinates induce differential forms, and in this case, they also induce what we call holomorphic differential forms. Holomorphic differential forms dz1 then to dzn. What are these guys? What do they do? So one thing they do, very importantly, is that they span, they are covectors. At every point they define for me a ring of covectors, and they span a very important complex space at every point of my complex manifold X, which is called the holomorphic cotangent space. The holomorphic cotangent space. So at every point P, which is the same thing as just a tuple of Z's in my C to the n. What is this? So let's give some notation. I'll write this by T sub P star X, the usual notation. All this is it's very simple. It's just the span. It's the linear span over the complex numbers, C, of these covectors, d, z1, d, zn. So, again, to be more explicit, these are complex vectors, complex linear combinations. T1 and Tn are just complex numbers. That's what I mean by the span sub C. It's the complex span. And so, you know, if you're not very familiar with differential geometry, this notation might seem slightly weird. You can think of this picture, what I wrote here, and you can think of these as your abstract vectors. Just like in usual linear algebra, you know, you have a vector space spanned by some abstract vector v1, v2, v3. Well, this is my notation for v1, v2, v3. It's just that the reason we write it like this is because these vectors behave in a very special way when I change coordinates, and we'll get to this in a second. Right, so as a kind of side remark, which we will return to in a bit. So if I think of c to the n in terms of real differential geometry, so if I think of it as r to the 2n, now maybe call it, so this is kind of notation that I will reuse several times. So when I think of when I'm looking at a complex manifold called X, and I suddenly want to look at the underlying real manifold, where I'm sort of forgetting about the complex structure, I will put this little subscript r on it. So just like here, we have c to the n, but if we forget about the I, then it's just r to the 2n. And so, yeah, right, so the real coordinates, you know, the relation is that the kth z coordinate decomposes in the standard fashion, and so the real cotangent space that you're possibly more familiar with from your differential geometry course, so real cotangent space, which I will call T P star of X sub R. What is this? This is just the real span. This is just the real span of your familiar differential forms coming from the real coordinates. So dx1, dy1, up to dxn, dy. How are the two things related? So how is this, you know, what I'm calling the, maybe I should say complex. There's nothing really, this is just a vector space at a point. So it's a complex cotangent bundle. They will fit into a complex cotangent space. They will fit into a holomorphic cotangent bundle. But this will come in a second. So the complex cotangent space, how does it relate to the familiar notion of real cotangent space? Well, what we have is, so we have this, because of this decomposition of Z into the real and imaginary part, these vectors, these covectors, dzk, they also decompose into the real and imaginary part. And so in other words, they're just linear combinations, but now with complex coefficients of these real covectors that we're familiar with. And so these guys belong to, from this point of view, I could say, so as I said, they are just linear combinations of vectors in here, but no longer with real coefficients, right? Because I'm explicitly including I here. So I need to complexify my space. So the way I would write this is like this. So I have TP star X sub R. And what does it mean to complexify? Well, if you've seen this construction before, this will become obvious. If you haven't, just take it as a notation. So I'm just tensoring this with complex coefficients. So, in other words, this is just the span, the linear span of the same covectors, dx1, dy1, down to dxn, dyn, but now no longer with real coefficients, but with complex coefficients. And let me give this space another notation, which I will reuse later. I'll call this lambda, capital lambda sub p, capital lambda 1 sub p of x. So, you would be forgiven if you thought that this lambda 1 sub p of x, the complexified real cotangent space, is just the complex cotangent space. The complex cotangent space is the complexified real cotangent space. But you would be wrong. Let me explain why.
So, for dz to be holomorphic, don't you need some extra assumptions on dx and dy? Or
For what? For z?
or dz?
For dz to be holomorphic. Well, I mean, at this point, they're just vectors. I'm not talking about any holomorphic structure yet, right? Or covectors.
You introduce them as holomorphic differential forms.
That's right, that's right. So I'll get to it in a second. I mean, the reason they're holomorphic differential forms is they're holomorphic sections of the holomorphic cotangent bundle, right? So, but I'm not there yet, so just hold your horses. Right, so, okay, so notice that this complex cotangent space, which I denoted by TP star x, it certainly is a subspace of this complexified real cotangent space. But it is not equal to it, not even close. Reason being that, you see, this is a real vector space of dimension 2n, right? And so when I complexify it, I get a complex vector space of dimension 2n. Because these are still treated as linearly independent vectors, just now with complex coefficients. This is a 2n, complex 2n dimensional, this is a complex 2n dimensional vector space. But this guy is complex n vector space. It's half the dimension, half the complex dimension. Why? So why is this? I mean, this may sound very confusing, but once you kind of write this as spans, you realize, you know, as complex spans, as a subspace of this. Remember, this is the span of a complex numbers of these dx I, d, yi, right? But these guys here, they're also complex spans, but of very specific combinations of dxi's and dy. So I'm putting an important constraint. So these are spans of dxi plus I dyi. So you can clearly see this is a very much a subspace, half-dimensional subspace. And I will call this half-dimensional, like as a subspace of this complexified real cotangent bundle, as a subspace of that, I will give this another notation which mimics the lambda notation up there. And I'll call it lambda 1, 0 px. And similarly, So similarly, you know, I have this 2n dimensional complex space of dxi's and dyi's, and I'm looking at a subspace, half-dimensional subspace, where I'm considering these very specific combinations where I take dxi and I add dy to it with the coefficient I. There's a complementary way of combining these vectors, complementary in the sense that I get a complementary vector subspace, such that the direct sum of the two subspaces gives me the whole space. Where if I just change this from plus to minus, this is, you know, a very typical way of building a complementary space in a vector space. So if I look at the span over the complex coefficients of now dxi minus I dyi, this gives me a complementary subspace. Which I will call lambda p01 of x. And so what the complementary subspace means is that this complexified real cotangent space, lambda p1x, has this very natural decomposition into the 1, 0 covectors and the 0, 1 covectors. And sometimes we also say into holomorphic, purely holomorphic covectors and purely anti-holomorphic covectors. So, so I'll leave this as a remark for now. We'll return to this decomposition. We'll need it tomorrow. But now, yeah, so now kind of for today, my main interest is this subspace lambda 10 px, which is the complex cotangent space, right, or a fiber of the holomorphic cotangent bundle. So Tp star x, these things are what we call fibers of the holomorphic cotangent bundle. So if you've never seen vector bundles before, fret not. It's a really simple thing. So the notation is T star x, so I'm just dropping the subscript P to indicate which point I'm at. And this is there is a map. Well, okay, so what is this? By definition, this is just the total union, the disjoint union of all the complex cotangent spaces as I go over my entire manifold. Just take all these cotangent spaces, so just all these spans of dz's or dxi plus I dy. Just take all these vector spaces, put them together into a total union, and you get a huge set of junk. It turns out, although we won't discuss this, don't have time to discuss this in detail, it turns out that this is also a complex manifold in its own right, and it has complex charts and so on. But explicitly, it's really just a simple thing like this. You just take all the complex cotangent spaces, put them together. And of course, whenever we have a disjoint union over points in X, there's always a natural map back to X, which just tells me which point I'm looking at. Right, so there's a map down to X, and the way we like to write, at least in complex geometry, the way we like to kind of express what this vector bundle is by saying, well, so if I look at a point, some point P inside my X, then over this point is the fiber, and that fiber is nothing but the complex cotangent space. And this is a commutative diagram. So let me just say a few more words, which you can take as kind of definition of these words. So this is a holomorphic vector bundle with fibers being the cotangent spaces, the complex cotangent spaces, which are, each one of them is isomorphic to c to the n, right? Because, where is it? Here. If I just treat these as abstract vectors, I'm just looking at a span, a linear C span of n vectors. So that's a complex n-dimensional vector space. So that's just C to the n. And so that's why we call it a holomorphic vector bundle. That it's a bundle of spaces because we just bundle them all up together. And each space in this bundle is a vector space in its own right. Does that make sense so far? I'll give you a few seconds to absorb. Okay, so I call it a holomorphic cotangent bundle. The reason I do this is because, so X is a holomorphic, it's a complex manifold, a holomorphic manifold. Those two words are synonymous for me. So it's a complex manifold. And this, well, I didn't explain it, but it also has a natural complex manifold structure such that this map, this projection map, becomes a holomorphic map. So we have a complex manifold of dimension twice the dimension of X. Why is it twice the dimension of X? Well, the dimension of X is n, because in this particular example, I'm literally just taking c to the n. And I'm testing these spaces for every point in X. So there's like a horizontal dimensional direction, which is the same as the dimension of X. And then for each point in X, I have a fiber, which is an n-dimensional vector space. So if you like, this space almost quite literally is c to the n cross c to the n. So it's of dimension 2n. And this is always the case with cotangent bundles. You have a complex manifold of dimension n, some abstract, not necessarily c to the n, some abstract complex manifold of dimension n. It has a cotangent bundle, which is a complex manifold of dimension 2n. So everything always doubles. And so what we have here is a 2n-dimensional complex manifold mapping to an n-dimensional complex manifold by a holomorphic map. And so whenever we have stuff like this one, we have a bundle of this sort, what we like to do is take sections. So sections are just maps from X back to T star X, which compose to the identity. So, and these sections, we call them holomorphic differential forms. Holomorphic differential forms differential, maybe be more specific, differential, holomorphic differential one forms are the holomorphic sections of the bundle. So let me kind of try and draw this pictorially. Semi-pictorially. So the notation for holomorphic sections of this is usually omega, capital omega, 1 sub x. And, well, without going into too much technical detail, you can think of this as the total set of all local holomorphic sections. Meaning, we have this complex manifold T star X mapping down to X, let me call this projection map maybe pi. So what is a holomorphic local section? It's a map like this. S. So such that if I do this composition, so if I take a point in X, apply S, so I go up to this big manifold up here, and then project using pi, then that achieves nothing. It's just the identity.
Excuse me.
Yeah.
The blue is.
Oh, the blue, you can't see it. Yeah, sorry. Let's do maybe orange. Orange is better. Orange is better, yeah. So such that, so what was it? Pi compose S is the identity on X. Right. So it's a holomorphic map from X to T star X, which composes with pi to give the identity. That's what a holomorphic section is, or a global holomorphic section. The only other word that I'm going to include here is local, which means that this S, I don't necessarily insist that it's defined on all of X. It's okay if it's defined on some subset, some open subset. But the important property is this, that it kind of maps things from X up into T star X, but if I project it, then it's not doing anything. Yeah?
Or to like declare that this is a honest bundle, you need to upgrade it from local to global. So you-
Totally. Yeah, definitely, yeah. But I hope you can take my word for it. Okay, so let's. This is an important object. So we call this. So various names. I could say this is. I'll use this word without explaining because we don't have time for this. But this is the sheaf of holomorphic sections of the cotangent bundle T star X to X. Right, okay, so let me... Okay, we have this kind of somewhat slightly abstract definition of this omega 1x. Let me give you a bit more hands-on practical view on what this does. Basically, what do elements of omega 1x look like? Every element is a local section, local holomorphic section. And so that's what I will do. So at least as a set, you can think of this like this. It's the set of all elements that look like this. I'll call them omega. And omega is just a linear combination of my covectors, dzi. But the important thing is that this is a linear combination of the same covectors dz1 through dzn, but the coefficients, they are now more sophisticated than just complex numbers. They're complex numbers which vary as I vary the point z of my manifold P. So, and the way I want to, I want to restrict the type of variation I allow, and so I just want all these functions to be holomorphic on some open subset of X. So these are holomorphic functions on some open subset U of X. So in other words, Fi is a map. It's a holomorphic function like this. And okay, so one more notation. So this is a span of these differential elements, is another word that people sometimes use. These holomorphic differential elements, it's the span, but over the local holomorphic functions on x. The way I'll write this is as span sub x of dz1 through dz. By this subscript x, I just mean that the coefficients that I allow in this span are holomorphic functions locally defined on x. Does this make sense? I'll give you a moment to try and absorb this. Any questions so far? Okay, so then let's step up a gear. So I've explained to you what holomorphic differential one forms are. They're elements of this space, and each one of them is just a span over locally defined holomorphic functions of these differential elements, which you should think of really as just kind of vectors, local, abstract vectors, with some properties, which is why we have this strange notation for them, just like in usual differential geometry. But ultimately they're just vectors. So when we have a vector space of some dimensions, there's a famous construction called the exterior algebra, or wedge product. And so that's what we're going to do now. So I started with holomorphic differential one forms. Now let me look at holomorphic two forms. So I'll use similar notation, inspired, omega 2x. And what these are, again, thinking, I'll give you a kind of a description, very kind of hands-on description like this as spans. So what these things are, they are linear combinations with coefficients, which I'll call f, I, j, which are, again are holomorphic functions, locally defined holomorphic functions, etc., etc. But now, as my vectors, the things that I'm taking the span of are these wedge products. And, well, I guess I should write this. So, again, we're using this type of notation. I can write that this is the linear span over the locally defined holomorphic functions on x of these newly formed vectors dzi wedge dzj. Okay, and so, again, reusing some of the stuff that we may have learned in linear algebra, I can write somewhat loosely, but on some level it's completely precise. So because these vectors are just formed as the second exterior power of the vector space spanned by dzis, this is just omega 1x wedge omega 1x. Or, another notation that you see in linear algebra is capital lambda, or capital big wedge 2, the second exterior power. So second exterior power of omega 1x. Now, I appreciate that omega 1x itself is not really a vector space, right? Because, well, it's a span over some weird thing that is not a field or anything. But you really can make sense of it thinking, having that as inspiration and kind of everything you know about vector spaces and taking their exterior powers, doing it in this setting and really utilizing this word that I'm not explaining of sheaf theory, then you can really make sense of this very, very simply. For now, I hope you can just, if it's slightly confusing, try to kind of at least absorb the sense of what's happening. Okay, so another notation, or another way of thinking about it. So these omega 1x, they were local sections of the holomorphic cotangent bundle. So these, the second exterior power, these holomorphic 2 forms, are also holomorphic sections, local holomorphic sections of a bundle. And that bundle is the second exterior power of the cotangent bundle. So I'll write this like this. It's the set of local sections of what people call T, big wedge 2 or lambda 2 T star x. So where, say it like this, so the second exterior power of the complex cotangent space at P is really just the linear span, this time an honest linear span over the complex numbers, over these wedge products of your vectors. Oh, and once I present it this way, when you have a linear span over C of these, this is your second exterior power, it's very easy to compute the dimension of this. So T star x was the span. It was the span of these dz1 through dzn. There was n of them, so that vector space was isomorphic to C to the n. Here we have the exterior algebra. So this thing is, maybe leave it as an exercise, but it's what is it? N times n minus 1 over 2, I think. All right, so how's this? All right? Question? Okay, I'll give you a moment again to absorb this. Okay, so we have differential 1 forms, which are local sections of the cotangent bundle. We have differential 2 forms, which are the second exterior power of that. So we can keep going. We can take the third exterior power, the fourth, etc. up to, let's look at the nth exterior power. So this is wedge to the n of omega 1x. And, well, what are these? So let's give it again, our explicit description. So these are objects that look like this. Here we have holomorphic function, locally defined holomorphic function, which multiplies the only one vector that can be created using the nth exterior power when we have n vectors, which is this total wedge product of all the dz's. So, in other words, again, this is the span over x of just a single vector, dz1, wedge dz in. So because we have just, so maybe enumerate it like this. So again, these are the local sections of the nth exterior power of T star x, where if I look at the fibers of this exterior power, so T star x, T x, lambda to the n, the nth exterior power of this. This is the linear span over C of just one vector, which is dz1 wedge dZn. And so, of course, because it's a linear span of a single vector, it's a one-dimensional complex vector space. So it's really isomorphic to C. And so, when we were looking at T star x, its fibers were n-dimensional vector spaces, and I called that, T star x therefore was the bundle of these T star px. So it was a bundle of n-dimensional vector spaces. We would say that that is a complex vector bundle of rank n. So the dimension of the fibers, we call that rank. And in this case, this is a very special case where we have a complex vector bundle, which is just, you take all of these vector spaces and put them together for all p. But now, the fibers are one-dimensional complex vector spaces. And so we call that a line bundle. So omega n x is, if you want to be pedantic, sections of a line bundle over x. It's a very important line bundle. Say a couple of other words for about this. So we often call omega nx, this nth exterior power, we call it the top exterior power of omega 1x. Why top? It's because n here, this n is the same as the dimension of the manifold x. Remember, I started with x being c to the n, so it's the same as the dimension x. If I take any higher exterior power than n, then I ran out of vectors. I basically ran out of the wedge freedom. And so any higher power of omega 1x higher than n, strictly higher than n, all of those bundles are just trivial. They're just bundles of zero vector space. So here's the top exterior power of omega 1x, because omega, let's say n plus 1 x is just zero. There are no, the only vector that you can make out of wedging more than n of dz is the zero vector. So this, hopefully, is one way to convince you that this top exterior power is somehow very important. It's a very important object that is attached to our complex manifold, and indeed we call it the canonical bundle. So omega nx is the canonical line bundle, but when you say canonical bundle, you always are referring to this special line bundle. So I will never even include the word line. It's a canonical bundle of x, which in this case was just c to the n. And by the way, maybe another thing I should mention, because it's such an important object and it appears in so many different contexts, it does have kind of an enormous number of distinct notations. So it's worth notation. It's worth being aware. And sometimes in the same paper you will find it denoted by several distinct notations. So, you know, sometimes people call it omega n, sometimes people call omega top x, sometimes people will write just capital omega x, sometimes people would write lowercase omega x. Another very common notation is k sub x. And there's probably more. These are the most common. So, you know, everything I discussed, I mean, I kind of, I sort of used the fact that the complex manifold X that I started with is the complex space, the Euclidean space, C to the n. But not really. Everything I discussed is more or less, you know, if you replace C to the n with an abstract manifold, you can repeat almost word for word everything I said. Except this one thing, which I'll discuss now. So when X is equal to C to the n, there's something special about the canonical bundle that happens, that doesn't happen for most other complex manifolds. So this omega x, I'll use this notation, capital omega x for the canonical bundle. So omega x, in the special case when x is C to the n, admits a global section. Remember we talked about these bundles being sets of local sections. And it's important that we talk about local sections because in complex geometry, global objects rarely exist. Just because you need to glue things together over different complex charts, and the assumption that things need to glue in a holomorphic way is a very, very strict, very rigid assumption, and so it fails very often. So global things in complex geometry rarely exist. But not in this case. In this case, we do have a global section. And not just a global section, but also a nowhere vanishing global section. Nowhere vanishing global section. What is this nowhere vanishing global section? Well, you could guess it yourself. It's just this total wedge product of dz's. Zi's are the canonical coordinates that are given to me because I'm looking at C to the n. So these dz's are canonically associated with these coordinates, and I take the total wedge product of that, and the global holomorphic function, which is, you know, this f, where is it? This f is just the constant function 1. It exists on C to the n. It's a perfectly nice holomorphic function. So that's it. So the way we write it is that we use this kind of cohomological notation to say that it's a global holomorphic section over all of x of the bundle omega x. This is the notation that we often use. And what is this global section? I mean, if you forget about the fact that we're talking about complex things and just think back to your differential geometry, when we integrate over manifolds, right, we need to take the top degree wedge form. That's the thing that we need to integrate over the manifold. And so this is the analogous object to that. It's the differential form which is amenable to integration in the complex sense. So it's the volume form. It's the volume form of our complex manifold. So it's called a holomorphic volume form. On X. So in other words, this complex manifold X, the Euclidean space C to the n, has a special property in that it has a volume form. I can take this volume form and integrate integrate over it and get some kind of version of volume.
Quick question.
Yeah.
Is zero, like cohomology zero, wouldn't make sense to be n?
No, it's if you think of this as a sheaf of vector spaces, then it really is the zeroth cohomology of that sheaf, or the zeroth cohomology of X with values in that sheaf. So that's the explanation for the notation. But yeah, you can just think that H0 means global.
Like the Dirham cohomology as in...
Yeah, that's exactly right. Or another thing that you can think of is like check cohomology. When you have check cohomology, you want 0 cycles. 0 cycles are the global things, right? 1 cycles are the things that are defined on double intersections. So I would, if I were interested in that type of thing, I would look at H1 of X with values in this. Yeah. Right, okay. So let's talk a little bit more about this volume form. So what happens if I change coordinates? I have c to the n and it has a canonical coordinate z, right? That's how I start. But now suppose I change a coordinate. Suppose I have w. So another coordinate on c to the n. Then what happens? Well, I can, now I have c to the n with some other coordinate w. I can repeat literally everything I said by replacing by replacing z with w everywhere, and the story would just code through word for word, right? So then what I would end up with, when I get to this bullet point, is that I get a volume form, which is the total wedge of the w's, right? So now by just changing a coordinate, I got another volume form, and so obviously there's an obvious question: how does this volume form relate to this volume form? And well, you can think about it. These dz's, this is where it comes, the perspective of the fact that these vectors that we're taking wedges of dz's, that they transform under coordinate changes in a very particular way. They transform by the Jacobian of the coordinate change. That's where this becomes really, really important. These are not just abstract vectors, they're abstract vectors with properties. So one thing you can check, maybe as an exercise, is that the way it relates to the volume form in the z coordinate is that you get the Jacobian determinant out of it. So you have, dw by dz, that's my notation for the Jacobian matrix, and then you just need to take the determinant of that. And maybe one thing that's important to note, if we have a change of coordinates, if it's an honest change of coordinates, remember back to your calculus, multivariable calculus, the Jacobian of a change of variables is an invertible matrix. It's a matrix of full rank. And so you would therefore expect this determinant to be a non-zero, nowhere zero function. So this volume form was a nowhere vanishing form, and this form is also nowhere vanishing form because they are related by a nowhere vanishing function. Does that make sense? Question? No. Right. Okay. So that's good. Right, okay, so now we can sort of, now that I've told you this story by focusing on c to the n, we can try to extrapolate, and it's not so difficult to, more general manifolds, so more generally. So any complex manifold X has a holomorphic cotangent bundle. holomorphic cotangent bundle. Still, we have the space of local sections of that holomorphic cotangent bundle. So these are local holomorphic sections of T star X over X. And this happens to be a vector bundle of rank n. And so if I take the nth wedge power of this vector bundle, I will get a line bundle. And so the definition is that the canonical bundle of X is the top wedge power of the holomorphic cotangent bundle. N, where n is the dimension of X. Okay, so that's the canonical bundle. What about these volume forms? So, once X is not the Euclidean space anymore, then all bets are off. There's no reason to expect this line bundle, this special line bundle, to admit a global, nowhere vanishing section. It might admit plenty of global sections, but they might be zero. So it's both properties are important. The fact that it's globally defined and the fact that it's nowhere vanishing. As we saw with this, with this calculation, the fact that we had two volume forms and they're necessarily related by some global nowhere vanishing function. So that's an important property. And so for general complex manifolds, that is just not the case. It just doesn't happen. And we will see an example of this. But that does mean that there's an important subclass of complex manifolds which do have this property. They do have the property of having a global volume form. Yep.
I'm still a bit confused by this H. So what is the cochain complex that you're considering for?
Okay. So it's a long story, right? Because you have to treat this as a sheaf, and if you treat this as a sheaf, how are you going to take the indeed, what is the cochain complex? So what you need to do is you need to take a resolution. You need to take an injective resolution of this sheaf, and so once you now have an injective resolution, it basically becomes a 2x2 array where in one direction you have the injective resolution that you've picked, and in the other direction you have, for instance, the this is a line bundle. Anyway, the important thing is to take this injective resolution, and then you have to take the hypercohomology of that resolved complex. And so this H0 is, by definition, the zeroth hypercohomology of your resolution. So then you need to check that H0 is independent of the resolution that you've picked. And so that's why I get away by using ordinary H0 notation. But of course, that's a mini course of its own. Right. So, So what I was saying is that we have, we kind of have identified that there's an important subclass of complex manifolds which may have this property of admitting a volume form. Not all of them do, but some of them do, and so these are the ones that actually we'll want to focus on. So we say that this canonical bundle, omega x, is trivial if it admits a nowhere vanishing global section. So in other words, i.e., if X admits a volume form. So this now explains another set of words in that definition that I wrote at the very beginning of the Calabi-Yau manifold. Remember, it was some kind of complex manifold, and then there was the clause of with trivial canonical bundle. So this is the property that a Calabi-Yau manifold needs to have. It needs to be a complex manifold with other rubbish, but in particular, its canonical bundle needs to be trivial. It needs to have a volume form in order to deserve the name Calabi-Yau. All right, so let's talk about examples.
So in a sense, you have several usage of trivial, no? Because before you used trivial for saying that your bundle was just a zero element.
That was a that I misspoke.
Ah, okay.
Yeah, so maybe it's better to call that a zero bundle, although that's not a standard terminology. Trivial bundle really means you have a global nowhere vanishing section.
And is that the only bundle? I mean, this top
No, there are plenty.
canonical bundle is the only example of trivial, or can you have another bundle that can be also?
Plenty of trivial bundles. Plenty of trivial bundles. Simple, non-simple. Yeah. I mean, it's a. In fact, this is not the usual definition of what a trivial bundle is. It's just for line bundles, this is an equivalent way of saying it, which is relevant for us. But again, you know, that is a super important, interesting topic that deserves a mini course of its own. So I'm trying to skip. Right. Okay. So examples. So example 0, which we've just spent a lot of time discussing. So for the Euclidean space. You know, the canonical bundle is the span over X of this kind of canonical volume form. And this thing is trivial, and so again, for those of you who have seen some differential or algebraic geometry before, this will make sense. Otherwise, just take it as notation. So when I say that something is trivial, I will write this, that it's isomorphic. This is the trivial line bundle on X. Also called the structure sheaf, whatever. All right. So now, first interesting example. So the other example of a complex manifold that we considered were these complex tori. So for a complex torus, so if I have this, which remember was just c to the n mod lambda. So okay, let's think about this guy. So so this is a quotient of c to the n by a lattice, right? Now c to the n has a volume form. So the volume form dz1 which dzn on c to the n. Let's see what happens with this volume form when we attempt to take the quotient. What is the quotient actually doing? The quotient is translating points in c to the n by integer amounts. Right? These are discontinuous, kind of discrete changes, right? So if I look at this volume form at some point z, and then I look at this volume, the value of this volume form at some z plus lambda 1, the differential element dz1 would become dz1. So like d of z1 plus lambda 1. But lambda 1 is just a discrete it's not a continuous variable. It's just a constant. So d differentiation of it will just kill it. This is a very heuristic way of explaining it, but it it has the essence of truth. So, in other words, what I'm trying to say is that this volume form on c to the n is actually invariant under lambda shifts. And so since it's invariant under lambda shifts, it has perfectly well-defined sense of having a value at any equivalence class in this quotient, because it's the same value. So in other words, what we say here is that this volume form descends down the quotient. So this thing is translation invariant. And so that means it descends to a volume form on X, on this complex torus. And so what we have is omega dz1. I'm not even going to bother giving it some other kind of notation. I mean, it literally is this wedge product of z, and it's invariant under translations. And so this gives me a global holomorphic section over the whole complex torus of the canonical bundle. So that means that the canonical bundle of any complex torus for any integer lattice lambda is trivial. For any lambda. Okay, so this gives you another example of a holomorphic manifold with a trivial canonical bundle. Oh, and by the way, again, if you look back at the very first definition, the definition of the Calabi-Yau manifold, so some of the important words there was that it was a compact complex manifold blah, 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 with a trivial canonical bundle. Just a second. With a trivial canonical bundle. This example 0, although the canonical bundle is trivial, X, which is C2, is not compact. So this is definitely not going to give us a Calabi-Yau manifold, no matter what. It's not compact. This one, on the other hand, is compact. It's a complex torus. And it has trivial canonical bundle, so it's a genuine candidate for a Calabi-Yau manifold. Yes, so there are, I think, a number of questions.
So I'll do the egoist pick again. Does the lattice have to have nearly independent?
Yes. Yes. Generic. Yeah, otherwise problems arise. So generic just means linearly, all the lambdas are linearly independent. Was there another question? Okay.
So, even though you can't find a global charge, you can always find a global volume form.
That's right, that's right. But if you think also, all the charts, like, remember what I was suggesting, so we have this picture of this parallelogram. Like this, right? And what I argued was that there's no way we can sort of cover the whole parallelogram, including the boundaries, in a one-to-one fashion, but we could cover them with kind of smaller parallelograms like this. But these parallelograms would be translations of one another. And so even though, even though this is, strictly speaking, I'm writing this in some kind of local chart of this complex torus, its expression in the other chart would be, I would just need to translate all the z's by some constant amount. And so, again, the formula is just going to be unchanged. Okay, so let's see an example where we don't have a volume form. So for X being the projective space, So first, let me just focus on the case n equals to 1. Just to make things simpler. So in this case, x is P1, and it's the set of tuples in homogeneous coordinates like this. And so also here, what we have is the canonical bundle of P1. Now this is a one-dimensional complex manifold. So actually the top exterior power is the power of 1. So in this case, the canonical bundle is the cotangent bundle itself. There are no higher exterior powers. So it's literally just, or if you like, it's the first exterior power of omega 1x, which is the same thing. So, okay, so recall that we have these affine charts. So we had U0, which was, remember, it was the one where Z naught was not 0. I identified it with a complex Z plane. And then we also had the other affine chart where Z1 was not 0. And I identified it with the complex W plane. Right, and so Z was just Z1 over Z0, and W was Z naught over Z1. And so importantly, we had, because now we have these two complex charts, one with coordinate z, one with coordinate w, and we have a transition function. So with transition function, which is, it just relates z with 1 over w, or w with 1 over z. So that means, so now let me try to describe the canonical bundle, which is the cotangent bundle, locally over these two charts. So I will write it like this. So, omega 1, let me write it like this. Omega 1x restricted to u0. This is just span over functions locally defined on u0. Maybe I'll write it like this. Span over u0 of the obvious holomorphic differential dz, which comes from the local coordinate z. Similarly, over u1, we have the same kind of story. So omega 1x restricted to u1 is really just the span over holomorphic functions locally defined on u1. Span of dw. Right. Okay, so how do these two things relate to one another? So here at this point I'm basically simultaneously trying to show you what's happening over P1 and teaching you how to work with vector bundles. Tall ask, but bear with me. Okay, so you could say these are local trivializations. That's what we say. This is some kind of line bundle, omega 1x, or some kind of line bundle on x, and I'm giving you a local presentation in terms of something completely obvious. It's a span of a single vector. So that's what we say, it's a local trivialization. And what I need to tell you next, in order to fully describe this line bundle in a global way, is to tell you how these local trivializations, how these local expressions glue to one another. So just like with coordinate charts, we have transition functions. Here we have transition functions as well, from one trivialization to another. So what I need to tell you in order to give you a description of omega 1x is to tell you the transition function from one trivialization to another. So let's do that. So if I look at omega 1, so maybe let me give these a name. Omega 1 u0 and omega 1 u1. Just restrictions of omega 1x to these two affine charts. So now I want to tell you how they glue. And they glue over the double intersection. So omega 1 u0 restricted to the double intersection u0 u1. And the other guy, omega 1 u1 restricted to the double intersection. Now we have, so to speak, two line bundles, two kind of differently presented line bundles, but over the same space, which is the double intersection. And so I am going to give you the relationship, which is an isomorphism like this. So the local generator, as we say, the local generator, the basis vector for this restriction, how does it relate to the local generator, which is for this bundle is dw? So how does dz relate to dw? Well, let's just change the variables, right? What else could it be? So it's really, you could say it's dw of z. What the hell does this notation mean? It just means that I need to differentiate. Sorry, which way do I want? It's dz of w. That's what I want. Well, whatever. dw. So what I mean by this is that I need to compute the derivative of z with respect to w, and that's the coefficient in front of the basis vector dw. Right. So that's how this change of variables goes. Again, it's helpful to, in order to pass through these kind of manipulations, it's helpful to at least momentarily detach yourself from the global geometric picture and polymorphic structures. Just think of these as vectors. I have one vector space with a basis vector, call it v1. And I have another vector space, completely different vector space, with another vector, basis vector, called v2. And I'm just giving you a linear isomorphism between these two one-dimensional vector spaces. And the formula for this isomorphism is that it takes vector v, what did I call it, v1, to vector v2 with this coefficient.
Shouldn't it be dz of w?
dz of w, yeah. That's why I got confused. Yeah. Right. Okay, so that's the formula. Okay, but now we know how z depends on w. Where is it? Here. We know that z of w is 1 over w. So we can actually compute this derivative. Let's see what we get. So this is it's d by dw. How do you write this? D by dw of 1 over w times the basis vector dw. Right. And so this guy becomes minus dw over w squared. And herein lies the problem. You see, we started with this perfectly innocent dz candidate for a volume form. So, in this chart, u0, this is a perfectly nice volume form. It's a volume form on C, C to the n where n equals 1. Right? And it's nowhere vanishing. It has all the right properties that would qualify it as a volume form. But the problem is that this volume form on this affine chart u0 does not extend as a volume form to the other affine chart, because it transforms, its transformation, its expression in the other affine chart has a problem at w equal to 0, which is a valid point inside my other chart. So there's no way to extend this Never mind nowhere vanishing. It doesn't even extend as a holomorphic thing. It has a pole. So So what we observe from this simple calculation is that dz has a pole of order 2 at, well, the point z equals to infinity, or w equals 0. And the conclusion that we can draw from this is that dz does not define a global non-vanishing section of omega 1, global nowhere vanishing. Section of omega 1s. In particular, dz does not define a volume form on P1. Of course, this doesn't necessarily mean that P1 doesn't admit a volume form at all. I'm just saying that this is the most obvious candidate for a volume form is certainly not it. So does P1 admit a volume form? Well, let's try and argue through this a little bit. So suppose I do get myself a volume form. So omega is a global section over P1 of the canonical bundle. Suppose this is a volume form. So what does that mean? That means, you know...
I think we're running out of time.
Oh, are we running out of time? Okay, so I will pick up here tomorrow evening. This is where we're going to get into the real interesting stuff about volume forms. So yeah, you can think about this. Anyway, see you tomorrow.